Welcome to the Deep Dive. We're the show that tries to cut through all that complexity in modern systems.
Right. There's just so much noise out there.
Exactly. We want to deliver those core insights you need fast, especially when, information overload is just everywhere.
And if you're looking for that shortcut, the way to get really informed without drowning in details, well, you're in the right place.
Yeah.
Today, we're diving deep into an architectural style that's really shaped software over the last, decade? Microservices.
Yes. That huge shift, right? From those enormous, sometimes really clunky, monolithic apps to something, more agile, smaller, self-contained units.
In our guide for this journey, we're leaning heavily on key excerpts from Sam Newman's classic book, Building Microservices.
It really is a foundational text. Holds up so well.
It does. Newman gives this incredibly practical, sort of holistic view, covers everything from, the initial design thoughts all the way to deployment quirks.
So our mission today?
Our mission is to pull out the absolute must-know nuggets from his work. So by the end, you'll really get what microservices are, why they're so dominant now, and crucially, what adopting them actually means in the real world.
And hopefully with a few surprising bits and, enough humor to keep you listening.
We'll try.
Okay, let's get into it then. At the very, very basic level, what are microservices?
Right. So Newman defines them pretty clearly. They're small autonomous services, and each one is really focused on doing one thing and doing it well, extremely well.
Okay, less like that complex Swiss Army knife.
Yeah, exactly. More like a whole toolkit of really specialized, super efficient tools.
Right. And the first question everyone always asks is, okay, small, but how small is small?
Yeah, the classic question. Newman's smart about this. He says, don't get hung up on line counts. Small in Java isn't small in Ruby.
Sure.
But he mentions John Eves from realestate.com.au, who had this great rule of thumb, something that could be rewritten in 2 weeks.
Wow, 2 weeks. That's really fast.
It is. It sets a certain scale, doesn't it?
So the goal isn't just being tiny for tiny's sake. It's small enough and no smaller. Like, it gets to a point where a system just doesn't feel too big anymore.
Precisely. Not too big to manage or change quickly or even, throw away and rebuild if you need to.
And that independent change and deployment piece sounds absolutely key.
It's fundamental. And to make that work, Newman stresses services cannot overshare their internal workings. If they share database tables or internal models too much,
They get coupled again.
exactly, you lose the autonomy. The network boundary actually helps enforce that separation.
Okay, so why did this shift happen? What were the big problems with monoliths that microservices aim to solve?
Well, the drivers are pretty strong. First up, there's technology heterogeneity.
Meaning you're not locked into one tech stack for everything.
Right. Microservices let you break free. Teams can pick the absolute best tool, maybe Ruby for one service, Java for another, Node for something else for each specific job.
That sounds liberating for developers.
It really is. And it's not just flexibility. Newman points out it actually unlocks innovation because teams use tools they're productive and happy with. And that, surprisingly, impacts business agility.
Okay, interesting link there. And what about resilience? That's always a huge concern.
Yeah, it's paramount. Newman uses the concept of bullheads. It's an idea from resilience engineering, like in ships.
The watertight compartments.
Exactly. Service boundaries act like those bulkheads. If one service fails, maybe it gets overloaded or has a bug.
It doesn't sink the whole ship.
Precisely. The failure is contained. Unlike a monolith where, one bad component can crash the entire application, microservices allow for graceful degradation. The problem's isolated, the rest keeps running.
That makes a ton of sense. Okay, and then there's scaling. That seems like an obvious win.
It is, but how it scales is the really neat part. With a monolith, right, if your login page gets hammered...
You have to scale the whole thing, even the parts doing nothing.
Exactly. Even if the reporting module is just sitting there idle, microservices let you scale only the specific services under load. Newman uses Gilt, the online fashion retailer, as a great example.
Oh, yeah, I remember that.
They started with a monolith in 2007. By 2009, it was really struggling with traffic spikes. They moved to microservices, and by 2014, they had over 450 services, each scaling independently.
450, wow.
Yeah, and it massively improved their ability to handle traffic and control costs using things like AWS for on-demand scaling.
So targeted scaling equals cost efficiency. That's powerful.
Huge. Another big plus is ease of deployment, because services are independent.
You can deploy them one by one.
Yep, deploy service A without touching D or C, That dramatically cuts the risk and the coordination nightmare you often get with big monolithic releases.
And it sounds like this changes how teams work, too. Better organizational alignment.
It really does. Newman points out that it encourages small, autonomous teams to own the entire life cycle of their service.
From idea to production and beyond.
Exactly. Design, build, deploy, operate, maintain. It boosts focus, accountability, ownership. You see this model in places like Amazon and Google.
Okay. And lastly, composability and replaceability. They're like building blocks.
Like Legos for software, yeah. If a service isn't cutting it anymore, or maybe a better technology comes along, you can just swap out or rewrite that one block. No need to rebuild the whole castle.
Okay, so given all these benefits, is this just a new name for something old, like service-oriented architecture, SOA? I remember that buzzword.
That's a fair question, and Newman addresses it directly. SOA, he says, had sensible goals, reusability, maintainability.
Wow.
But there wasn't really good consensus on how to do SOA well. It led to a lot of pitfalls, often heavy-handed implementations with things like enterprise service buses becoming bottlenecks.
Ah, the dreaded ESB.
Right. So Newman positions microservices not as replacing SOA, but as a specific approach for SOA. Think of it like XP or Scrum are specific ways of doing agile. Microservices are a specific, maybe more opinionated way of doing SOA. Learn from experience.
That's a really helpful distinction. So how do they stack up against other ways to break down code, like, say, shared libraries or modules?
Also good questions. Shared libraries are great for code reuse within a system, but they don't give you that technology heterogeneity or independent scaling. Plus, they create a shared dependency, change the library. You might have to update everything that uses it.
Right, lockstep changes.
Exactly. And modules like OSG in Java, or maybe Erlang modules, they offer some internal structure and lifecycle management, but you're still generally limited to one technology stack, and scaling is usually still monolithic. OSG in particular, Newman notes, often ended up adding more complexity than it solved.
Okay, so microservices really push that independence and choice further, but we should probably say it's not a magic solution, right? No silver bullet.
Absolutely not. Newman is crystal clear on this. Microservices are not a panacea. They bring their own challenges, especially around managing distributed systems. Complexity shifts from inside the services to the interactions between them. It's always about trade-offs.
This shift to microservices, it must really change the role of the architect, right? We often compare software architects to, building architects or civil engineers.
Yeah, and Newman pretty much says those comparisons are, inaccurate, maybe even dangerous.
Dangerous? How so?
He argues that traditional architects and engineers work with a level of rigor, established practices, even liability. That's just different in software. In the UK, an architect can be sued for bad advice. Their knowledge goes back centuries, millennia even.
Whereas software
is fluid. It changes constantly. Newman has this brilliant line. If bridge building were like programming, halfway through we'd find out that the far bank was now 50 meters farther out. That is actually mud rather than granite.
Ah, okay, that paints a picture.
So yeah, we're kind of stuck with the word architect, but we need to redefine what it means in our context.
So if not a building architect, then what's a better metaphor?
Newman really likes Eric Dornenberg's analogy. The architect as a town planner, like playing SimCity, basically.
The town planner. Oh, explain that.
Yeah. Well, a town planner doesn't design every single house, right? They don't specify the color of every front door.
No, they set up zones, roads, utilities.
Exactly. They zone a city. For us, that means defining service boundaries, the big picture. And they focus intensely on how things move between zones, the communication protocols, the data flow, not necessarily micromanaging what happens inside each zone. The goal shifts from creating a perfect, static end state to building a framework where the system can emerge and evolve over time.
That's a really powerful shift in thinking. And part of that, Newman mentions Frank Bushman's point, is making the system habitable for developers too, not just users.
Absolutely critical. It's about creating an environment where developers can actually be productive and, dare I say, happy, which leads directly to Newman's strong advocacy for the coding architect.
Meaning architects need to actually write code.
Yes. Not just draw diagrams. They need to spend real time coding with the team, ideally pairing on regular tasks, normal stories. It keeps their decisions grounded in the reality of the code base and helps them understand the actual impact of their architectural choices. No ivory towers allowed.
Makes sense. You have to feel the pain points yourself.
Yeah.
So how does this town planner architect put this vision into practice?
Yeah.
Newman talks about a principled approach to architecture.
Right. It starts with connecting everything back to strategic goals. Why are we building this? Faster time to market, global scale. The architecture has to serve the business strategy.
Okay, strategy first. Then
Come principles. These are like guiding rules that align actions with those goals. A principle might be, say, delivery teams have full lifecycle control of their services, or the system must be portable across cloud providers.
high-level rules
Yeah.
and below principles.
Our practices. These are the more detailed, often tech-specific guidelines that make the principles concrete. Things like use REST over HTTP for synchronous comms, or all services must emit standard health check metrics, or capture logs centrally using this format. Practices bring the principles to life.
And they probably change more often than principles.
Much more often as technology evolves. Newman makes the nice point that one person's principles are another's practices. It's fluid. But the key is having those overarching ideas guiding the evolution, plus enough practical detail so teams know how to actually build things.
So a big part of the architect's job, then, is defining what a good citizen service looks like in this ecosystem. How do you balance autonomy with cohesion?
That's the balancing act, exactly. A good citizen service needs, first off, solid monitoring. You absolutely need coherent cross-service views of health, not just isolated data points, standardized metrics, centralized logging. These are non-negotiable.
And clear interfaces, presumably?
Vital. Clear contracts for how services talk to each other. And finally, architectural safety measures built in to prevent those cascading failures we talked about. Making sure one service misbehaving doesn't bring everything down.
How do you enforce these standards without being overly bureaucratic? Newman suggests governance through code. What does that mean?
It's about moving beyond just documentation. He talks about exemplars pointing teams to actual, working, real-world services that get things right. Not some perfect theoretical example, but a living piece of code that demonstrates the principles in action.
Like a reference implementation.
Exactly. And related to that is the idea of tailored service templates.
Pre-built starting points.
Yeah, pre-configured code skeletons that make it easy to do the right thing from the get-go. Maybe a template already includes your standard logging library, integrates Hystrix for circuit breaking, or hooks into your metrics system like Drop Wizard's metrics for graphite. It lowers the barrier to adopting best practices.
But he has a big caution there, right, about who creates these.
A huge caution: avoid having a central architecture team just dictating frameworks through code. That kills morale and innovation fast. Defining practices and creating these templates should be a collective activity, maybe managed like an internal open source project. Mandated frameworks are often poison.
Right, collaboration over dictation. And that brings us back to the perils of shared code. Newman has that controversial rule about DY.
Ah, yes, the famous one.
Yeah.
Don't violate DRY. Don't repeat yourself within a microservice, but be relaxed about violating DRY across all services.
It sounds wrong at first. Why relax DRY across services?
Because, Newman argues, the cost of coupling introduced by sharing code, especially shared domain objects, like a customer object library used by multiple services, is far, far worse than the cost of some code duplication. If you change that shared customer object,
You might have to update and redeploy every single service that uses it.
exactly, or deal with horrible message queue issues if the format changes. It creates hidden dependencies and brittleness. Shared internal helper libraries, like for logging, are generally fine because they don't leak across service boundaries. But shared domain code, very dangerous territory. You want services to be independently changeable.
So it really sounds like this evolutionary architect role is incredibly multifaceted.
It is. Newman sums it up with keywords like empathy, collaboration, adaptability, ensuring autonomy, and enabling governance. It's about understanding trade-offs, working with teams, guiding evolution, and constantly balancing freedom with responsibility. It's a dynamic, ongoing process.
Okay, so we understand the what and the why and the architect's role. Now, how do we actually design these microservices? How do we find the right boundaries? Newman points strongly towards domain-driven design, DDD.
Yes, specifically Eric Evans's concept of bounded contexts. DDD is really the key toolkit for finding those sensible boundaries within your business domain.
So what's a bounded context in practice?
Think of it as a specific area of your business with its own consistent language and models. Newman uses his MusiCorp example. The finance department and the warehouse are distinct bounded contexts. They talk to each other through well-defined interfaces, but internally, they each have details and terminology that only make sense within their own context.
They hide their internal complexity from each other.
Exactly. And Newman mentions nested bounded context, this idea of turtles all the way down.
Meaning context within context.
Yeah. You might identify a large, coarse-grained context, but realize there are smaller, more specific contexts nested inside it. The decision on whether to model those nested ones as separate top-level services often comes down to organizational structure.
Conway's Law again. If different teams manage those nested parts.
They probably should be separate top-level services to maintain that team autonomy and clear ownership.
And the big benefit of decomposing along these bounded contexts is that they align with business concepts, right?
Yep.
So business changes are more likely contained.
That's the goal. If the business rules for warehousing change, ideally only the warehouse service needs modification. It minimizes the ripple effect.
But there's a warning here, too.
A very important one. Newman cautions strongly against prematurely decomposing a system into microservices, especially if it's a brand new domain where the boundaries are still fuzzy. It can be incredibly costly to get those boundaries wrong early on.
So counterintuitively, maybe splitting existing monolith is sometimes easier.
He suggests it can be, yeah. Because you already know the domain, you've lived with it, you probably have a better feel for where those natural seams lie, even if they're tangled up right now.
Okay. So once we've hopefully found good boundaries, the next big challenge is integration, making them talk to each other effectively. What are the ground rules?
Pretty standard good API design principles, really. Avoid breaking changes like the plague. Keep your APIs technology agnostic. Don't expose internal tech choices. Keep them simple for the consumer. And, crucially, hide your internal implementation details. Protect your boundaries.
And then the fundamental choice, synchronous versus asynchronous communication.
Yeah, big fork in the road. Synchronous calls request response are often easier to reason about initially. You make a call, you get an answer or an error right away. You know if it worked.
But the downside?
The caller is blocked waiting, and if the downstream service is slow or fails, it can impact the caller directly, potentially cascading failures if you don't have things like timeouts.
Okay, so asynchronous.
Asynchronous is more complex technologically, usually involving message queues or event streams, but it's great for decoupling. The sender fires off a message and doesn't wait. Essential for long-running jobs, improving responsiveness, especially for UIs or mobile, and generally better resilience as the sender and receiver aren't tightly time-coupled.
Newman uses a great example to compare orchestration versus choreography for integration styles. Can you walk through the customer creation example?
Sure. With orchestration, imagine you have a central brain, maybe the customer service. When a new customer is created, it makes direct synchronous calls out to the loyalty point service, then the email service, then the postal service. It's like a conductor leading the orchestra.
You're souling the whole flow.
Exactly. The downside, that central orchestrator can become a god service, a huge bottleneck, and a single point of failure. And the other services tend to become anemic CR-root services, just dumb data holders told what to do.
Okay, so choreography is different.
Completely different philosophy. With choreography, the customer service just publishes an event. Hey, customer created. It shouts it into the void, maybe onto an event bus.
And other services listen.
Right. The loyalty service, the email service, the postal service, they are subscribers. They hear that event and independently decide what to do based on it. It's much more significantly decoupled, like dancers reacting to the music individually.
The downside there.
The overall business process is now implicit, spread across multiple listeners reacting to events. It can sometimes be harder to see the end-to-end flow or debug issues across services. Trade-offs, always trade-offs.
Let's talk integration technologies. ArcPC remote procedure calls seems like a natural fit for service-to-service calls.
It seems like it, yeah. RPC tries to make a remote call look just like a local function call, hiding the network complexity.
But Newman warns against this.
He does, because local calls are not like remote calls. Network latency, potential failures, marshalling overhead, they're fundamentally different beasts. And worse, some RPC frameworks rely on binary stub generation.
Meaning code gets generated for the client based on the server.
Yep. And this can lead to tight coupling and lockstep releases. You change the server's interface slightly, maybe remove a field.
And you break all the clients instantly unless they regenerate and redeploy.
Exactly. It forces everyone to upgrade together, destroying independent deployability. Newman also mentions expand-only types. You can add fields, but never safely remove them. It's brittle.
Okay, so what about REST? That's everywhere on the web.
REST representational state transfer is generally preferred. It focuses on resources like customers 1, 2, and 3, standard representations like JSON, and uses the standard HTTP verbs get, post, put, delete meaningfully.
And within REST, Newman really emphasizes HADOS. That sounds complicated.
HADO is hypermedia as the engine of application state. Yeah, the name isn't catchy, but the concept is powerful.
How does it help in practice?
Think about browsing Amazon. You don't have the URL for your shopping cart hard-coded, right? You click a link or a button that the site gives you.
Right. The site tells me where to go next.
HADOS brings that idea to APIs. Instead of clients hard-coding specific URIs to perform actions, the server includes links within the response data that tell the client what actions are possible next and the URIs for those actions.
Ah, so the server guides the client.
Precisely. This provides a huge amount of decoupling. The server can change its URI structures internally, but as long as it provides the correct links with understood meanings, the client doesn't break. Clients navigate by following links, not by relying on out-of-band, hard-coded information.
That's a really cool idea. But REST over HTTP isn't perfect either.
No, nothing is. You don't typically get automatic client stub generation like with some RPC frameworks. Implementing hypermedia well requires discipline. Some older web servers or frameworks might not support all HTTP verbs cleanly, like put or delete. And for very high-frequency, low-latency internal calls, the overhead of HTTP headers might be a concern, pushing you towards maybe a binary protocol just for that specific interaction.
Okay. And for those truly decoupled, asynchronous event-based systems?
Message brokers like RabbitMQ or Kafka are the usual suspects. They handle publishing events and managing subscriptions reliably. Newman stresses the smarts and the endpoints idea. Keep the middleware dumb, put the logic in your services.
Don't build logic into the bus itself.
Right. He also mentions ADAM feeds as a REST-compliant way to publish events that consumers can poll. But building robust async systems is complex, and Newman hammers this home. Correlation IDs are absolutely vital.
The unique ID that follows a request across multiple services.
Yes, for tracing and debugging in logs. He warns they're difficult to retrofit later, so build them in from the start. Seriously.
This leads to thinking about services as state machines.
Exactly. A service shouldn't just be a dumb data container. It should own all logic associated with behavior in its context. It manages its own state transitions, enforces its own rules, avoid those dumb, anemic services.
Okay. And briefly, reactive extensions.
RX. RX is a different paradigm for handling asynchronous streams of events. Instead of you requesting data, you sort of observe the outcome and react when something changes. It's about composing asynchronous operations in a declarative way. Powerful, but a different way of thinking.
Now let's revisit that tricky area, managing shared code and data. We talked about the DRY rule.
Don't violate DRY within a microservice, but be relaxed about violating DRY across all services. Still sounds weird, doesn't it?
It does. But the reasoning is the high cost of coupling from shared domain libraries.
Exactly. That accidental coupling is the greater evil. He also flags issues with client libraries, libraries provided by a service for consumers to use. They can leak server-side logic, restrict technology choices for the consumer, and again, force lockstep upgrades. Ideally, clients control when they choose to update their dependencies.
What about access by reference? Passing IDs instead of whole objects?
Yeah, instead of sending the whole customer object to the email service, just send the customer URI, like customers 1, 2, 3. The email service then fetches the details it needs when it needs them.
Pros and cons?
Pro avoids sending potentially stale data around. Con increases load on the source service, the customer service here, and can impact performance. Caching becomes really important if you use this pattern heavily.
And versioning APIs, how do you evolve them without breaking everyone? Semantic
versioning, SEMVer, major-minor patch, is key. Major version bump means breaking change. Minor means backward-compatible new features. PATCH means backward-compatible bug fixes. It communicates intent clearly.
And how do you manage the rollout of breaking changes? Major versions.
The preferred strategy is to coexist different endpoints. Run the old version, V1, and the new version, V2, side by side for a period. Consumers can migrate from V1 to V2 at their own pace. This preserves independent deployability. Newman does warn that supporting, say, 3 different versions simultaneously can become operationally very painful.
Finally, interfacing with users and third parties. How do UIs fit into this?
UIs often act as compositional layers. They might talk to multiple microservices. Patterns include API composition, a dedicated UI backend service orchestrates calls, UI fragment composition, different parts of the UI are rendered by different backend services, or the popular backends for front ends, BFFs pattern.
A backend tailored for a specific front end.
Exactly. Like a BFF for the mobile app, another for the web app. The big caution Newman gives with BFFs is they should only contain logic specific to delivering a particular user experience, UI formatting, data aggregation for that specific view. Don't let core business logic creep into them, or they become another kind of monolith.
And dealing with third-party software, fun and fleas. Always fun.
Yeah. Often necessary, but Newman highlights the usual pain points. You lack control over the vendor's roadmap and decisions. Customization is often surprisingly more expensive than bespoke development, and you can end up with integration spaghetti due to proprietary protocols. Best advice: insulate your core systems from third-party specifics as much as possible. Treat them like volatile external dependencies. #TAG5e, splitting the monolith and tackling persistent data.
Okay, let's talk about the big one. Splitting that monolith, that big, scary, giant presence that so many teams face. How do you even start chipping away at it?
Newman brings in Michael Feather's idea of finding seams. A seam is basically a place in the code where you can start to separate things, to treat a piece in isolation.
And where do you find these seams?
Newman says bounded contexts make excellent seams. Those natural business capability boundaries we talked about earlier, those are your prime candidates for splitting.
So identify the context first. How did the Musicorp example go about it?
They started by identifying those high-level domains: catalog, finance, warehouse, recommendations. Then it was an incremental process, slowly refactoring code, moving related classes into new packages representing these contexts.
Not a big bang rewrite.
Definitely not. And using tools like Structure 101 to visualize dependencies was key. It helped them spot wrong interactions, like maybe the warehouse code was directly calling finance code, which it shouldn't. That analysis helps solidify where the true boundaries should be drawn.
But the absolute hardest part seems to be the database dilemma. Splitting the data. Newman calls databases tricky beasts.
Understatement of the year, maybe? They are incredibly difficult to untangle. The first step is just identifying what code accesses which parts of the database, and then maybe splitting out repository layers that align with your target service boundaries.
But what about things like foreign key relationships between tables that will end up in different service databases?
That's a huge challenge. You lose that database-level integrity enforcement. That constraint, Newman says, becomes a constraint we need to now manage in our resulting services. Often it requires a business decision. What should happen if an order refers to a catalog item that gets deleted? Do you prevent deletion? Cascade the delete. Mark it inactive. It's no longer automatic.
And performance concerns too, right?
Yeah.
Multiple database calls instead of one big join.
Absolutely. Fetching related data across service boundaries can be much slower.
What about simple shared static data, like country codes?
Options there. You could duplicate the table in each service's database, but then consistency becomes a headache. Newman often suggests treating it as code, put it in a property file or an enum within the service. It's simple, deployment consistent. Creating a dedicated service just for country codes is usually overkill.
Okay, and shared tables, where, say, customer info and order info are all tangled in one table used by different parts of the monolith.
Yeah, this happens a lot. You need to identify those implicitly modeled concepts. Maybe that customer info really belongs to a distinct customer-bounded context that just wasn't explicit before. You need to make it concrete, eventually creating a customer service that owns that customer data. Same for things like generic line item tables or the catalog items, inventory items. They probably represent distinct concepts needing separate ownership.
Now, transactional boundaries, this sounds like a distributed systems nightmare. How do you ensure consistency when an operation spans multiple new services?
It is a nightmare if you try to use traditional distributed transactions like two-phase commit across services. Newman points out they're incredibly hard to implement correctly, especially managing locks and failures in a distributed environment. Java's transaction API tried, but it's complex and has limitations.
So, if strict distributed transactions are generally out, what's the alternative?
Eventual consistency. You embrace the idea that the system might be temporarily inconsistent across services, but will become consistent at some point in the future. Newman argues this is much easier to build and scale.
But what if you really need immediate consistency for a specific operation?
For those rare cases, you might need compensating transactions. If one part of a multi-service operation fails, you need logic to actively unwind what just happened in the parts that succeeded. For example, if creating an order succeeds but the payment fails, you need a compensating transaction to delete or cancel the order. It gets complex fast, especially if multiple steps need unwinding.
So what's the overall recommendation?
Stick to local transactions within a single service boundary whenever possible. If you genuinely need transactional behavior across services, Newman suggests modeling the transaction itself as a concrete concept, like an in-process order state. This gives you something explicit to monitor and manage the life cycle of that cross-service operation.
Okay. Last hurdle in this section, reporting challenges. Data is scattered everywhere now. How do you run reports?
Yeah, traditional reporting approaches often break completely. Trying to do data retrieval via service calls works for maybe simple real-time dashboards, but try running a complex query for, say, 24 months of customer purchase history across thousands of customers by hitting individual service APIs.
Forget it. The APIs aren't built for that, and it would be incredibly slow and inefficient.
Exactly. So Newman discusses data pumps as an alternative. This is a standalone process that, and this is a very specific exception to the no shared database rule, directly accesses the database of the service, read-only, ideally, and pumps that data into a dedicated reporting database or data warehouse.
But isn't accessing another service's database directly a huge anti-pattern?
It normally is. But the key caveat here is that the data pump must be owned, built, and version controlled by the same team that owns the service and its database. They understand the schema and can evolve the pump alongside the service. He mentions Netflix's Adjust This project, which pumps data from Cassandra backups into Hadoop for analytics, as an example of doing this well at scale. It allows services to own their operational data while still enabling offline centralized reporting. #tag V, deployment and testing for microservices world.
All right, shifting gears again. Let's talk deployment and testing. Getting these things out the door reliably. Continuous integration, CI, must be the starting point.
Absolutely. The basics still apply. Frequent check-ins, automated tests validating every change. But the crucial mapping for microservices is Newman's recommendation. One microservice per build.
One build pipeline per service.
Yes. To enable that independent deployment we keep talking about, he strongly warns against giant monolithic repositories and builds that try to build all services together. That just creates coupling and bottlenecks again.
Even for new projects.
He concedes a single build might be okay temporarily for a brand new system with lots of churn, but it must be seen as a transitionary step towards independent builds.
And CI naturally flows into continuous delivery, CD, and build pipelines.
Right. CD extends CI by modeling the entire path to production. Every check-in that passes the automated tests is considered a release candidate. And again, in a microservices world, that means one pipeline per service. Much better visibility, faster feedback, lower risk releases.
Okay, what about the actual artifacts for deployment? What are we actually deploying?
There's a range. You've got platform-specific artifacts like Java JRs, Ruby gems. These often need separate process managers like system supervisor and maybe configuration management tools, Puppet Chef, to get them running.
Then maybe operating system artifacts.
Yeah, like RPMs or DEB packages. These can be simpler because you leverage the OS's built-in tools for installation, dependencies, upgrades, uninstalls. It often simplifies the deployment process itself.
And then custom images, like VM images.
Exactly. Things like AWS AMIs, you bake in the OS, dependencies, and the service code itself into a single image. This speeds up provisioning massively and enables the immutable server pattern.
Immutable server.
Yeah.
Meaning you never change a running server.
Correct. Need an update? You deploy a new server from a new image and destroy the old one. No configuration drift, much more predictable deployments.
And where does Docker fit in all this? It's everywhere.
Docker builds on that idea, but uses lightweight containers instead of full VMs. Newman describes it as a platform built on top of lightweight containers. You package your app and dependencies into a Docker image, run it in a container. Docker itself manages provisioning, networking on a single machine, and provides registries. He calls it like a simple PaaS that works on a single machine.
But for multiple machines, you need more.
Right, you need orchestration layers like Kubernetes or Nomad or CoreOS Fleet to manage containers across a cluster. That leads to containers as a service, or CASAs. Docker really streamlined the packaging and running part.
What about managing different environments? Dev, test, staging, prod. How do you keep them consistent, yet handle their differences?
It's tricky. Production will look different, more hosts, load balancers, maybe multiple data centers. Test might be a single host. Newman says the balance between production-like environments and fast feedback isn't fixed. You constantly adjust based on where bugs are escaping. Automation is key to managing the configuration differences.
And the service-to-host mapping. One service per host. Multiple.
Newman has a strong preference here. While multiple services per host might seem cheaper or simpler initially,
It brings problems.
yeah. Technology conflicts, one needs Java 8, another needs Java 11 on the same box. Resource contention, potential for weird shared state issues. He strongly favors the single service per host model, ideally using those immutable images or containers.
Even though it means more servers to manage.
Yes, because it's significantly easier to reason about isolation and resource usage. And good automation largely mitigates the pain of managing more instances. It aligns perfectly with the immutable server pattern.
And if you want abstract away even the host management, there's platform as a service.
Exactly. Tools like Heroku, Cloud Foundry, Google App Engine. You deploy your code, the platform handles the provisioning, scaling, load balancing. Newman mentions guiltandrealestate.com.au had great success using PaaS to accelerate their microservice adoption. It lets teams focus more on the service logic.
How important is having a standardized deployment interface?
Crucial for automation. Newman stresses needing a uniform interface to deploy a given service, maybe a single script or command line call. This interface would take environment definitions, often in files like YAML, that map services to the required resources, CPU, memory, network, storage, credentials. He mentions Terraform as a promising tool for defining infrastructure as code across different providers.
Okay, deployment sorted. Now, testing microservices. This sounds way harder than testing a monolith. How do you ensure quality?
It definitely requires a different approach. Newman references models like Merrick's testing quadrant and Mike Cohn's test pyramid to think about different test types: unit, service integration, end-to-end, and cross-functional tests. The big emphasis is automate, automate, automate. Manual testing just doesn't scale here.
Unit tests are still the foundation, though.
Absolutely.
Yeah.
Smallest scope, fastest feedback, great for validating individual components and supporting refactoring. They should catch most logic bugs within a single service.
Then service tests. What's their scope?
These test a single service in isolation. But critically, you stub out downstream collaborators. So if service A calls service B, your service A test uses a fake service B, a stug or mock, that returns predefined responses. This lets you test service A's logic without needing a real running service B. Newman mentions Mountebank as a tool for creating these programmable test doubles.
Okay, that makes sense. Then we get to the really tricky end-to-end tests, the ones that test the whole system flow.
Yeah, these are the ones everyone wants for confidence, but Newman highlights major downsides. They are slow, often incredibly brittle. A small UI change can break them, hard to diagnose why they failed, and prone to being flaky. And he says flaky tests are the enemy because teams stop trusting them.
And there's an ownership problem, too.
Big time. Who writes them? Who maintains them across potentially dozens of teams? Dedicated test teams often become bottlenecks. A free-for-all doesn't work either. And Newman warns about the meta-version trap, thinking, okay, this specific combination of service versions pass the end-to-end test, so let's deploy them all together.
Which kills independent deployability again.
Exactly. It forces a lockstep release. His advice: limit end-to-end tests. Focus on test journeys, not stories. Test the absolute critical user paths, but don't add a new end-to-end test for every single feature or bug fix. Keep the suite small and reliable.
So if end-to-end tests are problematic, what's a better way to ensure a service change won't break its consumers?
Consumer-driven contracts, CDCs. This is a really powerful pattern Newman champions. The goal is to ensure that when we deploy a new service to production, our changes won't break consumers, but without needing to run tests against the actual live consumer systems. How does that work? The consumer defines its expectations of the provider service as a testable contract. This contract is then run against the provider service during the provider's CI build. If the provider makes a change that breaks the contract, violates the consumer's expectations, the provider's build fails before it gets deployed.
Shifting the verification earlier into the provider's pipeline.
Exactly. It's faster, more reliable, and puts the responsibility where it belongs.
Yep.
Newman mentions tools like Pact, which came out of realestate.com.au, and Pacto that facilitate this contract definition and verification process.
Okay, and finally, testing after production. That sounds risky.
It sounds it, but it's actually about sophisticated release strategies. It involves separating deployment from release. You deploy the new code to production infrastructure, but don't send live traffic to it yet. You then run tests in situ, right there in the production environment, like smoke tests.
And if those pass?
Then you can start shifting traffic. Patterns like blue-green deployment fit here. You have two identical production environments, blue and green. Deploy the new version to green, test it thoroughly while blue handles live traffic. Once confident, you flip the router to send all traffic to green. Instant rollout, instant rollback if needed. Zero downtime deployments.
And canary releasing.
That's releasing the new version to a small subset of production users first. Maybe 1% of traffic goes to the new version. You monitor it closely for errors or performance issues. If it looks good, you gradually increase the percentage until all traffic is on the new version. Netflix does this extensively.
And Netflix takes it further with their Simian army.
Oh yeah. Chaos Monkey randomly terminates production instances. Chaos Gorilla takes out entire availability zones. Latency Monkey injects network delays. They deliberately incite failure to ensure systems are tolerant of it. It's about building anti-fragility, an incredibly powerful technique, Newman says, but requires significant investment and maturity.
So the overall mindset shifts from preventing all failures, MTBF, to recovering quickly, MTTR.
Precisely. Tests help reduce failures, but in complex distributed systems, failures will happen. So focus equally, or maybe even more, on mean time to recovery. How fast can you detect a problem and restore service? Blue-green, canaries, fast rollbacks, good monitoring, they're all key to low MTTR.
And don't forget cross-functional testing, CFRs.
Right. Testing the non-functional requirements, performance, load, security, accessibility. Newman emphasizes that these are cross-functional requirements and need dedicated testing, often in production-like environments, run regularly against defined targets. Performance testing is a classic example. #tagged MED5. Scaling, securing, and organizing for microservices.
Okay, we've deployed, we've tested. Now, how do we keep these systems running smoothly at scale, securely, and keep the organization sane? Monitoring at scale seems like a huge challenge.
It is. You've got health data scattered across multiple services, multiple servers. The absolute foundation is central collection and aggregation. You need to gather logs, maybe using Logstash, Fluent, and application metrics, pushing to systems like Graphite, Prometheus, into central systems for a unified view.
Just knowing if a server is up isn't enough, though, right?
Not at all. You need semantic monitoring tests that simulate real user actions, synthetic transactions, to check if the business function is actually working, not just if the process is running.
And those correlation IDs we mentioned earlier become critical here.
Absolutely crucial. For tracing calls across multiple services through those centralized logs, Newman repeats the warning. Difficult to retrofit later. Plan for them up front.
You also need to monitor dependencies.
Yes. Monitoring the health, response time, error rates of services you depend on is vital. Libraries like Hystrix can help automatically track and react to downstream health.
And standardization is key for making sense of all this data.
Essential. Consistent log formats, standard metric names across services. Otherwise, your aggregated data is just a mess. And importantly, consider the audience. What does operations need? Alerts. What does support need? Dashboards. What does management or capacity planning need? Trends. Newman envisions a future where operational and business metrics are unified so you can see the direct impact of system performance on business outcomes.
Okay, let's switch to security in a distributed system. This feels way more complex than securing a single monolith.
It definitely introduces new challenges. For authentication and authorization, especially user login, you often look at single sign-on, SSO. SAMA is the mature enterprise standard. OpenID Connect is newer, REST-JSON-based, arguably simpler, but adoption is still growing.
An SSO gateway can centralize this.
It can, but Newman warns it can also become a single point of failure and might make isolated testing of services harder if they always depend on the central gateway. Trade-offs again.
What about securing calls between services?
Various options. Basic auth over HTTPS is simple. Client certificates provide stronger identity. For service-to-service, you might use SAML OpenID Connect with dedicated service accounts. Keep permissions minimal, make them easy to revoke. You could use cryptographically signed requests, like HMAC, or simpler API keys just for identification and maybe rate limiting. Directory services can manage identities.
And the deputy problem, what's that?
That's the tricky challenge of how Service A, when calling Service B on behalf of User X, can securely tell Service B that the request originated from User X. Passing the original user context downstream securely is, Newman notes, often a bit of a nightmare to get right.
What about securing data at rest? Encryption.
The golden rule applies universally. Don't write your own crypto. Use standard, well-vetted algorithms, AES 128256. Use salted password hashing. Never store plain text passwords. Key management protecting your encryption keys is critical, and absolutely encrypt backups, a very common oversight.
And Newman emphasizes defense in depth.
Yes, multiple layers of security, network perimeter, internal subnets, host firewalls, OS hardening patching, security modules like a Parmer or Linux, securing the application itself. Don't rely on just one layer. He uses Music Corp to show applying different techniques, HTTPS, client certs, API keys, selectively based on risk and sensitivity.
This brings us neatly to Conway's law and system design, the famous people problem.
Yes, Melvin Conway's 1967 observation. Any organization that designs a system will inevitably produce a design whose structure is a copy of the organization's communication structure.
The classic example, if you have 4 groups working on a compiler, you'll get a 4-pass compiler.
Exactly. Newman cites studies comparing loosely coupled open source teams versus tightly coupled commercial product teams, and examples like Netflix and Amazon showing strong evidence for this law. The communication pathways heavily influence the resulting architecture.
So the huge implication for microservices.
You need to structure your teams to match your desired service boundaries. You need to align service ownership to co-located teams, which themselves are aligned around the same bounded contexts.
Service ownership by small, autonomous teams.
Yes, teams responsible for the full life cycle. It dramatically increases autonomy and speed because they control their own destiny, reducing cross-team dependencies.
How do you handle code or services that multiple teams might need? Shared services and internal open source.
That's one model. Have a core team own a shared service, but allow other teams to contribute improvements via pull requests, managed by the owning team as gatekeepers. It requires good tooling, like Git code review systems, and a collaborative culture. It balances shared needs with clear ownership.
What prevents services from becoming orphans if a team disbands or priorities shift? The orphaned service problem.
If teams are aligned to stable business contexts, the ownership naturally remains with the team responsible for that context, even if active development slows down. It's less likely to become truly orphaned than if ownership was project-based.
The realestate.com.au case study illustrated this well.
Perfectly. Their squads were aligned to lines of business, LOBs, fostering deep domain expertise. This structure was a major factor in their success with microservices, directly applying Conway's law proactively. Newman also mentions the flip side, Conway's law in reverse, where an organization unintentionally restructures itself around a complex system design.
It all comes back to the fundamental people problem. Microservices aren't just a technical change.
Not at all. Developers need to become much more aware of things like network latency, failure modes, consistency models, operational concerns. Newman calls it a potentially rude awakening for those used to the simpler world of a monolith where operations was someone else's problem. It requires a broader skill set and mindset.
Finally, let's tackle microservices at scale. Embracing failure. That sounds so wrong. Software should not fail.
Ideally, yes. But Newman argues that at scale, failure is everywhere and inevitable. Think Google Scale components fail constantly. So instead of aiming for impossible perfection, infinite mean time between failures MTBF, you need to shift focus towards rapid recovery. Mean time to recovery MTTR. Embrace failure as normal, designed for resilience.
How much resilience is enough, though?
It totally depends. A 247 e-commerce site needs much higher resilience than an internal batch reporting system that runs monthly. You tailor the requirements. And degrading functionality gracefully is key. Understand the business impact of each service failing. If the recommendation service is down, maybe just hide that section of the page instead of showing an error. Make conscious choices.
And specific architectural safety measures help here.
Definitely. We mentioned timeouts, essential first step to stop waiting forever for a broken downstream service.
And circuit breakers.
Yes, like an electrical circuit breaker. If calls to a downstream service start failing repeatedly, the breaker trips or blows. Subsequent calls fail immediately, fail fast, instead of hammering the struggling service. After a timeout, it might let a single test request through, half-open state, to see if the service has recovered. Newman stresses latency kills and uses the Music Corp ad service example bringing down the site. Netflix's Hystrix library is the canonical example here.
Then bulkheads. Like on a ship.
Exactly. Isolate resources to contain failure. For example, use separate connection pools for calls to service B and service C. If service B goes rogue and consumes all its connections, it doesn't starve service C. Newman puts it nicely. Timeouts and circuit breakers help you free up resources, but bulkheads can ensure they don't become constrained in the first place. Techniques like load shedding, rejecting requests under high load, also fit here.
This all connects back to that anti-fragile organization idea, like Netflix.
Precisely. Their simian army deliberately, quote, incites failure to ensure that its systems are tolerant of it. By making failures common and expected, they force the system and the organization to build robust recovery mechanisms.
Okay, besides embracing failure, what are other scaling strategies?
You can go bigger, splitting workloads, separate critical functions from non-critical ones. These into real-time accounts versus batch accounts reporting. Spreading your risk, distribute instances across multiple physical machines, availability zones, even regions. Consider supplier SLAs. Load balancing across multiple instances is fundamental for capacity and resilience. And worker-based systems, using message queues, are great for asynchronous tasks or handling spiky workloads.
And scaling databases, the perennial bottleneck.
Always tricky. Distinguish availability, can I reach it, from durability. Is my data safe? Read replica scale, read traffic, but introduce eventual consistency. Sharding scales write traffic by partitioning data across multiple database nodes, common in NoSQL like Mongo, Cassandra. Adding shards can be complex. Beware of shared database infrastructure. Multiple service schemas on one database instance. It creates a significant single point of failure.
And caching, where does that fit?
Everywhere. Client-side, browser, proxy caches, CDNs, reverse proxies like Varnish, server-side, in-memory like Redis, Memcache. HTTP caching headers are built-in and powerful. Caching is vital for performance and resilience. A cache can serve data even if the origin service is down, if populated asynchronously. But Newman warns, keep it simple. Too many layers of caching lead to debugging nightmares and stale data. He tells a cautionary tale of cache poisoning due to bad headers, serving stale data indefinitely.
Autoscaling seems like the holy grail for handling load.
It's powerful. Automatically adding or removing instances based on load, predictive based on trends, or reactive based on current metrics. Essential for cost efficiency and handling unexpected spikes. But Newman stresses you must have good load tests to configure and validate your autoscaling rules before relying on them in production.
And the unavoidable CIP theorem. Consistency, availability, partition tolerance, pick two.
You don't beat math, as Newman says. In a distributed system facing a network partition, you must choose between strong consistency, C, or availability, A. AP systems, like many NoSQL databases, choose availability, sacrificing immediate consistency for eventual consistency. CP systems, like traditional RDBMSs in some configurations, choose consistency, potentially becoming unavailable during a partition to avoid inconsistent data.
Yeah.
The right choice. It depends entirely on the business requirements for that specific piece of data.
With all these dynamic, scaling, failing parts, how do services even find each other? Service discovery.
Crucial in dynamic environments. Simple DNS can work, but TTLs and caching can be problematic with frequently changing IPs, like with containers or autoscaling. Using load balancers provides a more stable endpoint. Dynamic service registries are often better. Services register themselves on startup and deregister on shutdown. Tools like Zookeeper, Console, etc. are common. Console is interesting as it includes health checking, key value store, and even a DNS interface. Newman's advice: don't write your own distributed coordination systems either. Use existing proven ones.
And don't forget, the humans need to understand this landscape too.
Right. You need tooling on top of registries to build dashboards and reports showing what services are running where and their status.
Lastly, documenting services. How do you keep docs up to date?
It's tough. Newman mentions tools like Swagger, now OpenAPI specification, for generating interactive API documentation from code or annotations. For Restera services, a hypertext application language provides a standard format for embedding links and discoverability, and tools like the HAL browser let humans progressively explore our APIs by following those links.
The ideal is a self-describing system.
That's the aspiration, where the system itself exposes its health, capabilities, dependencies, maybe even documentation links via standard endpoints, making the system inherently observable and understandable. #tag outro.
Wow. Okay, that was definitely a deep dive. We've covered an incredible amount of ground on microservices.
We really have. From the core ideas, the architect's changing role, integration patterns, splitting monoliths, deployment, testing, all the way to scaling and security.
It feels like the core principles kept coming up, though. Modeling around business concepts, automation, designing for decoupling, team autonomy.
Independent deployability, building for resilience, and making everything highly observable. Those really are the pillars Newman emphasizes.
And it's so clear it's not just a tech choice. It's a fundamental shift in how teams work, how organizations are structured.
Absolutely. That mindset shift towards embracing failure, optimizing for recovery time, MTTR over MTBF, that's huge. It's definitely a journey, like Newman says.
So, as everyone listening reflects on all this, here's that provocative thought we like to leave you with. Considering everything we've unpacked today, what's maybe one core assumption you hold about your own team's way of working, or maybe your systems design, that you might challenge now?
Or perhaps putting it differently, what's one small, really manageable first step you could maybe take this week to inject just a little bit more of that anti-fragile, resilient thinking into your own work?
Good questions to ponder.
Remember, learning this stuff is definitely a continuous process. This deep dive hopefully gives you a solid map, but it's just the start of exploring these ideas.
We certainly hope it's giving you a clearer picture and some practical insights for navigating the world of microservices. Thanks for joining us on the Deep Dive.
Join us next time.